Thank you very much, Idan, for organizing this event. As usual, your energy, your creative energy, managed to assemble together a fantastic program, socially, culturally, art, and science, and Orit and Varda for their help. I talked a little bit about theoretical, computational, brain prize last night. You saw the movies, some of you. You may have a chance, if you ask Orit, to show the movie again, those of you that want to see it. I'm going to talk today about learning and forgetting in brains and machines. Of course, you will see what computational theoretical research is doing, but it will be specific on, about learning and forgetting. This is ChatGPT suggestion for the slide. Sorry. Okay. So Albert Einstein, once you stop learning, you start dying. This is the topic of learning. This is from his lecture in Vienna. He didn't live in Vienna, but he frequently visited his colleagues in Vienna. And Sigmund Freud, what one forgets once, he will often forget again. Of course, this is the monument of Freud, was erected in 2018 in the Medical University of Vienna. And these two are among the founders of the Hebrew University, both Sigmund Freud and Albert Einstein. So this is learning, and this is forgetting. And I'm going to talk about several aspects of that vast area. I'm going to talk about the negative aspect of forgetting, which is known to be called is catastrophic forgetting. And I'm going to talk about them in two aspects. In one aspect is memory, or long-term memory, and the other aspect is continual learning. Okay, and as you'll see later on in the talk, memory and learning have different connotation or different meaning in modern research. Of course, there is no learning without memory. But memory is just memorizing events, memorizing stuff that you can recall later on. So it's a simpler task. Learning is more challenging because learning you have to acquire from experience, acquire new knowledge or new skills. So learning is much more challenging than just memory. And you will see in my talk going back and forth between learning and memory. So this is the negative aspect of forgetting, and I'll talk about ideas and algorithms, how to fight that, how to cope with catastrophic forgetting. And then I'll talk about the potentially positive aspect of forgetting, forgetting as a feature, not as a bug. Okay, so that's the two parts of my talk. I want before that to mention that there are passive aspects of memory which brains have to deal with because the brain is made of a biological tissue, and biological tissue degrades proteins, recycle, and so on and so forth. So there is a wear and tear of the tissue all the time, and that has to somehow maintain information throughout lifetime of us or an animal. That's a passive decay of memory traces. There's another aspect that brains have to deal with, which is all kinds of memory pathologies, amnesia types, and so on. Addiction is another pathology of memory that brains have to, and animals and humans have to cope with. This is the bread and butter of neuroscience research, experimental, clinical, cognitive, as Merab told us about. And this is most of the labs at ELSEC are dealing in some way or another about learning and memory, and in particular about also this aspect, like Naomi Habib, about Alzheimer's, Amit Sitri, about addiction, and learning deficits by Merab. And many of those research results you will hear here in other lectures. I'm dealing with some different aspect of forgetting, and this is I call active forgetting. Active not necessarily because we want it, but active in the sense that it is erasure of memory traces by interactions with other processes, as you will see later on. So that aspect of forgetting, the potential erasing of memory, even in machines that don't have to worry about protein decay and so on, have to deal with in brains and machines. So this is what I'm going to talk about. Memory, forgetting, which is inherent in memorization, inherent in learning, and the interaction between these active aspects of learning and forgetting. Please ask me if I'm not clear. All right. Okay. So we talked about that. So let me start with memory, the simpler type of learning. So there are two stages of memory. One is the storage of memory, how we encode, how we store memory in the network. And the other one is retrieving. So let me start with storing. So storing of memory is a simple process. When we have a salient experience, something that we see, we pay attention to it, or experience otherwise, it is stored in the neural circuit by the induction of small changes of many synapses in the network. And how is it done? So the simplest paradigm is what's known as Hebb, Donald Hebb, a neuropsychologist from 1940s. It's known as the Hebb plasticity rule. So if you have a pair of neurons, and the rule is that if this pair of neurons are fired together several times, then the connection between them strengthens. So this is the way the association is built into the brain. So this is for pairs of neurons, but now we have to think about not as isolated pair of neurons, but many pairs of neurons, or many neurons in a circuit with thousands or maybe million neurons in the brain or in machines. So here it is the way it works. So according to this hypothesis, so we have many neurons. Imagine that in one experience, the red neurons are co-active. And if they are co-active, then they undergo this plasticity, these changes in the connection between them, as it depicted here. It's not all the connections, but you see that this group of neurons form a memory ensemble or memory engram because all the connections between them are strengthened. I don't show here all the connections, not to clutter the picture. But that's the idea, that after this induction of memory, you form a memory ensemble, you form a memory trace which will store this memory for a long time. So how do we retrieve this memory? So here we have our memory ensemble within the big network. When a recalling cue activates part of a memory ensemble, so let's say I see a silhouette of a person, it reminds me of her, then the entire network is active to actually complete the information. So we have a recalling cue activate, let's say, these two neurons out of the ensemble. And then when it activates, because the connection between them strengthened, then the activity of this pair of neurons spreads to the entire ensemble, and the entire ensemble now is active, and that's the process of recalling the full memory. So that's kind of known as a pattern completion or associative memory, that because of the connection between the neurons, then association, something that reminds us about the whole memory, is able to recall the entire memory. So that's the simple paradigm, the simplest paradigm of how memories are stored and are retrieved in the brain. But the problem is that this is just a single memory. What happens if there are more than one? And what we are interested in more than one memory. So let's look now at a case where there is a second memory is stored. So now here it is, the empty circles will be a group of neurons that are now active or co-activated by a new experience that happens to activate together these groups of neurons, the empty groups of neurons. All right, so according to the same principle, now we have a second memory ensemble. The connections between the empty neurons are now strengthened, so we have now two memory ensembles overlaid in the circuit. Okay, so and the same idea that now if the recall, if a small group of the empty neurons become active later on during recall, then the entire second ensemble, the empty neuron ensemble, will be activated, fully activated, and will generate the recall of the memory. Okay, so that's a simple story. You can now go to 2, 3, 4 four examples like that, and this is the way one memory trace after the other is overlaid on the network, each one of them generating its memory ensemble for future recall. That's a very simple story. Now, the problem is, and that's a very important to note, that this second ensemble of neurons, the empty neurons, here, empty circles, are partially overlapping. They are not two different networks. They're in the same network. And because of the same network, so some of the neurons and some of the connections are common to the two ensembles. Like the connection here is common. There are connections which are not present here, but involve a subgroup of neurons. So in general, these different memory ensembles are not separate, are not in different parts of the network or different parts of the brain. That's the key point why forgetting is a problem. In any model, in the brains or in machines that work on the principle of distributed processing, of distributed memory traces, that the same network is storing a lot of information basically on the same group of neurons, as partially overlapping ensembles of neurons. All right, so the question is, this seems to be a call for failure. How many ensembles like that, overlapping ensembles, you can embed in a network before everything becomes completely confused? But let's first see an example of that. I'm not going to show you connections, it's really cluttered, but I'm going to show you an example of the retrieval of memory from a network that I simulated, where the network stored three memories, three patterns like that, and the recalling of them. So you'll see a square, and the square, each pixel is a neuron representing some information about the world. So here's an example. All right, so as you saw at the beginning, okay, let me start again. I start from something which is barely reminiscent of the image of Albert Einstein, but the dynamics of the network, the seed of the correct ensemble is spreading the information through the strengthened connections to the entire ensemble, and you get the full recall. Now, the same network, if I start from a different initial condition, in this case, I start with a network where this part is a name of a city, and then, again, the association, the spread of activity fills in the image with the landscape of memorized landscape of Copenhagen. So in this case, when I happen to see the word Copenhagen, it reminds me of the landscape of Copenhagen. This is another example. This will be a name of foundation and what the foundation does. So if you see this, if you activate this part of the network, then by remembering this is where you remember or you recall the fact that this foundation, among other things, is holding the Bain Prize. All right, so this is an example of three memories that are overlaid in the same network, and the way you initialize the network during the recall, that's the way that will lead you to the relevant memory. But the question is again, how many of this you can do in the same network? And for a while, initially, the suspicion was that this is going to be very inefficient, that this is going to fail very quickly because of this distributed nature. So to our surprise, and this is the first meaningful work that I did with my colleagues about memory in a neural network. This 1985. That's the first page of the paper. We found, to our pleasant surprise, that you can store infinite number of patterns in a neural network. Now, I want to emphasize that if I would have written it today, I wouldn't say infinite amount of memory, because there is nothing that in the physical limited world stores infinite amount of information. But what we meant by infinite amount, we meant that the number of memories scales with the number of neurons. So if you a small network, you can store a small number of memories. Okay, you increase the network, so in proportion to the increase in the size of the network, you also increase the number of memories. So that's kind of an efficient way to encode information. This is the picture of my colleagues, Daniel Amit, Zichrono Livracha, and Yibadel Haim Arukim, Hanoch Gutfreund. And this is perhaps one of the first papers that initiated the physics entry into neuroscience. And the reason why this paper was important is because it was perhaps the first research coming from theory that actually showed that you can actually use physics methods to make a quantitative, precise predictions. Like, okay, there is a story about memory, Hebb rules, and so on, distributed processing, but we want to know, is it efficient or not, and how many memories I can store in a circuit of a given size. So this is the result, or one of the main results in that paper. So what I'm plotting here on the y-axis is the accuracy of retrieval. So 1% is perfect accuracy of the memory, of the stored memory. 0 is just chance level, so it's complete failure. And in the x-axis is the number of stored memory, the number of memories that I stored in the process that I already described, divided by the number of neurons. Okay, so and the result is that there is a sharp transition between number in this regime. When the number of stored memories is smaller than 14% of the number of neurons, the precise number is not important. In this regime, you are below the capacity, so you memorize almost perfectly, and then above this regime, you forget completely, according to this theory. Okay, so I want to emphasize the forgetting here is not caused by a passive decay of memory traces, because in the model, nothing is decaying. The forgetting is due to interference between new and existing memory tracer, the way I explained. There's so much memories that you can load, that you can put on the same circuit to make sure that the interference between the memory traces is not horrible. Okay, so this is due to the distributed nature of memory representations. Okay, so there are good news about this and bad news about this. Well, the good news for us was that we can make a very concrete predictions and comparing different models and different paradigms using this methodology. The other good news is that if you are here below capacity, you don't have to worry, because really the performance is almost perfect. Okay? This is due to the nonlinear processing in the network. I won't discuss it today. The bad news is that beyond the threshold, everything is gone. It's like your circuit crashes, like your disk just is exploding or whatever. So this sharp transition, this is the kind of this is coined the notion of catastrophic forgetting. It's not only forgetting, but it's really catastrophe. You would like to have, okay, something happens here and maybe going like this, but this is just a sharp transition. Catastrophic forgetting, and that remains to be the coin that we're even using today in machine learning and in neuroscience, how to avoid catastrophic forgetting. I'll show different examples of catastrophic forgetting, but this is one of them, okay? Now you can say, okay, who cares? Maybe the brain is big enough and we are all living here and we're happy here. Could be, but it's not a good model for a memory. It's not a good scheme for memory. Okay, I'll show you two versions of a better behavior. One is catastrophic aging. So the y-axis is the same. The x-axis is different. It's not the number of memories per the number of neurons, but it's the age of memories. Okay, so I won't tell you for a while how we manage it, but this is an improvement. Well, this says the following. You can go on, learn new things, store memory, experience the world. Don't care about using only 10% or 90% of the brain. You can go on, storing, laying one memory trace after the other. That doesn't matter, infinite number of times. What will happen is, in this scheme, is that at any moment in time, you remember, you can recall almost perfectly all the memories that are more recent than, I would say, I don't know, 10 years ago or something, okay? So you remember everything that happened in the last recent 10 years. I'll just give a number. Okay, so this is what, but the problem is, again, beyond that, you don't remember anything. It's the same catastrophic forgetting, but now with age, not with the total number of memory that you overlaid, but with age. You can go on and storing and overlaying many, many memories, many, many experiences. At any given time, only the last 10-year worth of memories you can recall. Okay.
Let's define that you erase old memories. For each old memory that you erase, you can add a new memory.
Yeah. Or the other way around, for each new memory, you erase old memory, and I'll come to it. So how we achieve it, okay? How we go back, how we go and say, well, this memory should go down. So it's an automatic process. I'll discuss it later on in my talk, how to achieve it. Okay, this is in the early 90s, okay? A few years after the first catastrophic memory. Only a couple of years ago, with a postdoc, Israeli postdoc, Nimrod Shaham, unfortunately went to Mobileye later on, and Gabriel Kaiman, a colleague from Harvard Children's Hospital, we came up with something which looks more reasonable. So now the x-axis is the same, age of memories divided by the number of neurons, okay? But the scale is very different. Here it was 0.14, here it is 20, 40, 60. And you see at the beginning it's the same story, but the beginning is here. Here now you can actually gracefully forget. And the forgetting is in the retrieval probability. It's a stochastic process. Namely, you at any given time, there is some chance that you remember something that happened, I don't know, maybe let's call it 40 years ago, and there is some chance that you will forget something that happened maybe yesterday. It's a probabilistic thing, but nevertheless, the overall probability is a graceful decay. I won't tell you just a moment. I won't tell you how we achieve it. What is the secret? I'm just showing you the result of another algorithm, another mode of memorization that achieves this, which, at least from the perspective of modeling human memory, animal memory on the long time scale, maybe is reasonable, because that's what happens. Some memories from our childhood we remember, some recent memories we forget, but overall we can say that we remember better on average things that happens in the past than things that happens in the recent past than things that happens very early on. Yes.
Just a quick question so I understand that.
Yeah.
I'm guessing that important memory survives longer than trivial memory.
We'll come to it, not here. Here there is no, here all memories are the same, equally important.
But they use more neurons, important memories than trivial memories?
There could be, it could be. Or it could be that the encoding process that I mentioned is stronger in the sense that the strengthening of the connection in the encoding is more powerful during for important memories. Okay, but I'll come to the selectivity issue later on. Here it is more or less all the memories have equal status. Okay, good. Okay, very good. So now, the problem is with this that this may be okay to model memory system in the real brain or humans and animals. And we may not be so unhappy about it. Okay, we don't have to remember everything that happened to us. I'll come to that issue later on. But I want to switch now to learning. Well, learning, we would like to be able to learn things and then to remember them throughout our life. Okay, so that's not satisfactory. Okay, so what is learning? And in particular, what is continual learning? Continual learning is learning sequences of tasks. Okay, so each task is not simple memories, it's not simply memorizing an event. Each task itself is a considerable task for the circuit or for the brain or for the machine, like developing new skills, like learning new language, learning some new math, programming, driving, using of new technology. Each one of these is considered as a task. But throughout our life, we go through many sequences of learning tasks, okay? So this is the problem of continual learning, or this is the issue of continual learning. And there are other things like learning a new sport or activity, learn to swim, learn to ski, etc. Acquiring new knowledge in general, or things which formal education is sequential in its nature. We go from one grade to another, and we learn new things. So it's inherent in the way we use training and education. And it's also important even for the same basic task, but when the environment is changing, so you learn to drive in Tel Aviv, and then you go to, I don't know, to Scotland or to, the car, first of all, you have to drive in the wrong side or the right side, or the manners of the other drivers are changing, so you have to adapt. So it's another aspect of sequential learning, the basic skill, but you have to adapt the skill to new situations, new goals. You have other goals, you have other social contexts, and so on and so forth. So there are many important real life needs for continual learning. And needless to say, machines that would like to mimic the ability of animals and humans to effortlessly learn continuously one task after the other would like to do it also. But it turns out that this is a bottleneck for machines. And when I say machines, it's also a bottleneck for us, for computational and theoretical researchers, to explain how the brain does it, because we don't know the algorithms, or we don't even know, not only we don't know the algorithm that the brain is using, we don't even have a candidate, a good candidate, for an algorithm how the brain might do it. Okay, so it's a challenge, it's a question mark. And what I'm going to spend now in a few slides is what are the ideas that are around in this field of continual learning, how to cope with forgetting in the context of continual learning. So now it's not that I don't remember my birthday when I was 10 years old, but I should at least remember what I learned in terms of basic skills when I was young, and should be able to use it. Okay, so if you are not careful and you just use an algorithm that you learn that allows you to learn one task, and then you apply it again to another task, and so on, without taking care of anything, this is the catastrophic forgetting. So even after the second task in a sequence, you are not 100%, and then unlike the memory, you don't have even a grace period. You just have going on and on, downhill. And that's a fast decrease of performance on all tasks. This is what you do if you just use a canonical learning algorithm, a very efficient for learning one task. But then you apply it to another task, another task, another task, things go downhill very quickly. So how do we deal with this? Obviously, biology found a solution, but we don't actually have a good solution in terms of understanding. Okay, so here is in animation what kind of things happens or might happen, or what kind of things should happen when we learn sequentially three tasks. So performance here again, 100% is here, or at least some standard level, which is a good level, will be here. This is the first task, the second task, the third task. So we start with task one. We learn task one. The task 2 and 3 here our performance is baseline because we didn't learn them, clear. So, but we learned task 1, it's good, so it gets to a good performance. Now we come to task 2, Okay, so you see, we are able to learn task 2, but now task 1 suffers. Okay, that's the forgetting. Now in task 3, again, we learn task 3 very well, but then the 2 previous tasks suffer. Okay, that's the catastrophic forgetting that typically you'd see if you're not careful in your algorithm. All right, let's see what happens here. So if you see this, you say, well, let me be more careful. Let me make sure that the task 1, I'm stabilizing it, the weights, the synapses, I don't let them change. So, or change very little. So that's what happens here. Okay, so I learned task 1, everything is fine. I learned task 2, I cannot learn task 2 because I made the network too stable. And again, with task 3 again. So I'm not moving very much, okay? This is what's known as the plasticity stability dilemma or trade-off. You have a dilemma. You have to decide. Do you want a very adaptive and changing brain or circuit, or do you want something that is really engineered to keep all things fixed and frozen? Then you're not adapt. You don't learn new sequences. Plasticity, stability, dilemma. Okay, there are other things that you might want in your wish list, not only to solve this dilemma. So if you want to solve this dilemma, here it is, the ideal situation. We don't know how to achieve it, but that's what you would like. Would like to be the case that I learn task 1, then I learn task 2, task 1 is still perfect. Okay? I learn task 3, the 2 previous tasks perfect. That's what we would like to have to solve the problem. Okay, but there are 2 other things that we might wish to have. One of them is here. Okay, I learned task 1, but now the other 2 tasks are not baseline anymore. What's going on? What happens?
They're related.
What?
They're related.
They are related. So in other words, there is a transfer of knowledge, positive transfer of knowledge. Not only protecting things from forgetting, but actually transfer of knowledge. And similarly here, now you learn task 2, because of this transfer of knowledge, you actually do better than baseline, and task 3 and so on. So this will be a transfer of knowledge. Well, there is also this one which I might want. I learned task 1, like here, I improve on the other task. I learned task 2, see what happened to task 1. Task 1 not only didn't decay, but actually improved. So there is a transfer of knowledge in the other direction. And similarly here. So this will be a forward transfer of knowledge. This will be a backward transfer of knowledge. We would like to have these behaviors ideally, at least not in all circumstances, but in some circumstances. So these are the challenges, how to avoid catastrophic forgetting, how to resolve the stability plasticity dilemma, and if possible, even to have, on a positive side, forward transfer and backward transfer as well, at least in some situations. All right, so how to do it? So there's a vast literature in the last 20 years or so about this, and there are many possible solutions or hypotheses and algorithms. I'll describe very quickly, briefly, 2 of them. 2 classes of one. One is regularization of learning, and I'll explain what it is. Another one is replay, and I'll explain what this is. Regularization comes in two fashions, classes. One is weight, the synaptic weight, the strength of the synaptic weight regularization. Another one is architecture regularization, and then I'll talk about replay. So what is regularization? Regularization says that, okay, you learn task 2, but learned it in such a way that the changes in the synapses due to task 2 are small, so that there is not a big change in the overall pattern of connections. Okay, so this means regularized. You make it harder for the synapses to change, but not completely impossible to change. So you learn the task 2, you learn a new task while minimizing the changes in the synaptic weights that are coming from previous learning events. There is even a better, a smarter way of doing that. It's called intelligent synapses. This says the following. There is a way to actually, after I learn task 1, there is a way to estimate for each synapse Was it important for task 1 or not? If they were not important, feel free to change them for task 2. If they were important, be more cautious. So this kind of intelligent regularization. So let me illustrate it here. Okay, so let's suppose there are only 2 synapses denoted by theta 1. This is the value of synapse 1. Theta 2 is value of the synapse 2. And what I'm denoting here is the regime of weights that are very good for task A. So if you are here or here or here in this regime, task A is solved very nicely. So you learn task A, the first task, you are basically going into the middle in some typical value, which is somewhere in the middle. Everything is fine. Now comes task 2. And let's suppose task 2 has this regime of good behavior. Okay, so you want to be anywhere here in this ellipsoid in order to solve task 2. Now, if you are not careful, what will happen is that you first were here, and now you will just jump to a typical solution for task 2, which is in the middle of this regime here, which is obviously bad because then you are outside the regime of good performance of task 1. So that's the forgetting. So now, if you say, on the other hand, let me restrict the changes, then you may just not move much. So, okay, so you are still barely in this regime, but you don't learn task 2. That's the dilemma. Now, look what happens here. If you are doing this intelligent synaptic regularization, you realize the following. You realize that this direction, this synapse here, theta 1, really, you can vary a lot without changing very much the performance of task 1. On the other hand, if you move here, you have to be very cautious. But luckily, and statistically this happens in large networks, luckily, moving in this direction, okay, is not really important to actually solve task 2. You can just move here to the common regime along this direction, and you satisfy both type A and both task A and task 2. Now, this is of course a cartoon. You have to show it that if you do it in a big circuit in many tasks like that, you still have a regime, likely to have a regime where all of them are overlapping, all the region of solutions are overlapping. So by this method, you actually are more likely to get to, it's all statistics, but more likely to get to a regime where you are not losing too much of previous tasks. Yes?
What is happening, and the difference of what is happening between using an ancient memory and a very recent happening memory? What is the difference?
Well, again, I'm not talking about memory here, because memory, typically you have one point. This is not about memory. It's about task, okay? This is about learning a task. You learn a language. You learn a new skill, or you learn something, you learn to solve some new puzzle. There is a regime. It's not one collection of weights that does the job. In typical problems that you learn, there is a regime of parameters, in this case two parameters, but there is a regime that all of them will be fine. That's important because otherwise it doesn't make sense. Everywhere that you are here is fine for task 1. Everywhere that you will be here is fine for task 2. The sweet spot is the regime of parameters where both task 1 and task 2 are satisfied, and the challenge is to design your learning algorithm, your sequential learning algorithm, so that when you move from the solution here for task 1, you are more likely to get to this regime. So that's the kind of the story. That's what regularization is about. Okay. So okay. So that works in some cases, not always. The problem is that learning sequentially in a controlled way that we can test theories and algorithms and so on comes with a very different varieties. So, for instance, you learn to, here is an example where you learn to discriminate for many images, dogs versus cats. This is the same task, but in different statistics of images than this cartoon. This is real life images, this is just cartoons. This is another example, very popular in studies, in many studies. You learn to discriminate, to classify images from a digit 0, from images from digit 1. This is one task. The other task, forget about what this is. The other task is you learn to discriminate image 2 from 3, or image 4 from 5, or image 6 from 7, or image 8 from 9. So you learn sequentially this type of classification task. It's easy, it's relatively easy if all of them come together and you learn them together. But if they come sequentially, there is a problem. This is another example which is challenging. You have task 1 is to discriminate between 1 and 2 and 3 and 4. And task 2, you flip the labels. So now 1, 3 is in one class, and 2 and 4 is in another class. So because the images are not the same, they're almost conflicting. Not exactly the same, because the images here are not the same as here. They're slightly distorted. But this is an example where the two tasks are almost conflicting. Here it is basically the same task, but different statistics of input. Here the tasks are almost conflicting, and you can have many other cases of that. So the point which I want to emphasize is that if you look at the literature over the last decade or so, the problem is that you can choose this one and do numerical. You have good idea how to do it. You go to numerical simulations, it works fine. Then you ask, okay, what happens here? Well, it doesn't work. What happens here? Maybe it works. So there is a heterogeneity of behaviors and tasks. It's a zoo. It's really a zoo. So we need to have some understanding. Okay, so let me show you what happens. So for this case, this is task 1, task 2, and so on. What I'm showing you here on the y-axis to keep you awake is that the y-axis is loss, not accuracy. And because it's loss, the lower value is the better. Accuracy, okay? So this is the loss. This is the error, okay? Probability of error. So here's in this case, if you are not doing regularization, here it is, this curve is the performance of learning the task, after learning task 2, the performance of task 2, which is reasonable. On the other hand, task 1 is here, which is high loss. So you have forgetting on task 1. You learn task 1, you were here, but after learning task 2 is here, task 1 has much higher loss. This is the forgetting. However, if you are using regularization, then you see that if the regularization is strong enough, then the forgetting in task 1 actually disappears, and you retain both the performances of task 2 and task 1. So this is the demonstration of the working of the regularization. Regularization is still 0.1. If I'll go to regularization of 1 or 10, then task 2 will suffer, because I am now in the stable regime. I'm not allowing plasticity. But the good news is that there is a regime of regularization where I can retain the performance on the two tasks. So this is good news for the regularization. Okay, but here is an example which I already mentioned, that this is almost two tasks conflicting each other. And this is, no matter what you do with the regularization, task 2, after you learn task 2, task 1 is bad. You completely erase task 1. Okay, so sometimes regularization works, sometimes regularization completely fails. And unfortunately, many real-life problems are in this regime. Okay, in these cases where there is regularization may not be effective. All right, and some of our more recent work with students at Harvard actually tried to put a sense in this mess, and actually we came up from the theory, we came up with two guiding principles. One is, when the two input data are very different, but they have similar rules, but they're on a very different input data, that's good for regularization, because there is minimal interference. Because you have the same rule, in one task you learn it on this type of data, another task on unrelated data. It's basically one task, think about it like one task on two different sets of data. So in that case, regularization works. But if you have similar input data, but dissimilar rules, this is the worst case. That it's almost conflicting, right? Because the input data is similar, but now you're saying the rules are different. So this is where regularization fails. Okay, so what can you do for the difficult cases where you have almost conflicting or very hard way to keep the two tasks apart? So this is architecture regularization. Architecture regularization is thinking not in terms of the learning algorithm, but in terms of the architecture. So you basically allocate, you basically try to separate gently the memory traces of the task. So for instance, you say, well, I have big network, task one will also use these pathways, task one will use this one, or task one will use these modules, larger sections of the network. Task two will use other modules, somehow to move away a little bit from the distributed nature. Not everything is mixed up. You try to gently separate the architecture so that to accommodate learning. How you do it? Because how you know when you learn several tasks and now you come with a new input, how you know which pathway to use? Okay, so you have to have somebody to tell you, now you are in task one, use this pathway. Okay, so there is a problem here. So you need to have context, and the way we do it in recent work again by my group, we use what's called brain-inspired dynamic allocations with gating neurons. So what we have is we add to the network knobs, neurons that are vetoing the propagation of signals from other neurons. So you have, let's say you have a group of neurons here, they propagate information through a group of synapses to the next layer and so on, but now you have this gating, knob 1 and knob 2, that kind of are shutting the gate potentially. So if for task 1, let's say this one is 1, so it allows information propagation this way, but not this way because this is 0. Task 2 will allow, this gating unit is 1, it allows information passage through this pathway, but not through this pathway. Task 3 may be one that both of them are open, so they are partially overlapping the task, but the important point is that there is a contextual input that will tell the system when you come with some input, with some example, with some stimulus, with some image or some text, which pathway to use, because you have these gating knobs that get contextual information. There is, if you are driving in Israel, well, the weather, the people talk Hebrew, you know that you are driving Israel style. If you are in, in Edinburgh, maybe, you have a context, you know where you are, you switch to Scotland style. So you need that extra information for this to work. And here is the way it works. So this is the example that I said was a bad example, that regularization didn't work. You learn task 2, this is loss, task 2 is fine, task 1 is bad. But with gating, both tasks actually improve with the gating. This is the number of gating units. Both tasks improve, but they go together almost. So in other words, the performance on the two tasks improve, and there is minimal forgetting here. All right, does it work in the brain? Or this is something that is an ongoing project together with Dan Segev. I won't go into this detail. Maybe Dan will talk about it later in his talk. But anyway, Dan and his students are trying to actually map and find in the complicated circuit in the cortex, particularly inhibitory neurons that have these properties that they actually veto the propagation of information from other neurons. There are different cell types, and they act on different parts of the circuit. So that's something which is ongoing work, and we are hoping that we'll be able to learn from the cortical circuit to better design gating networks. All right, so architecture realization, the problem is we need a special hardware like gating units. We need a context signal, both in learning and operation, to tell the network now you are in task 1, task 10, and so on, and how to optimize the resource allocations. How many of them you need, to what extent they should allow to overlap, and so on and so forth. So this is an algorithmic question. All right, let me briefly talk about a completely different method, which is trying to avoid this regularization, this replay. What is replay? There are two types of replay. Let's talk about memory buffer. That's a brute force, boring solution. It says the following. in addition to the network that learns the sequentially task, you keep also a disk, a hard disk, a memory buffer, in a separate network. That memory buffer, you store in the memory buffer all the examples from the previous task, both the input and the desired output. Okay? So all this you store in the memory buffer. And what you do when you learn task 2, you interleave with the task 2 data, you interleave from the memory task 1 data. So now you are refreshing both of them. The network is big enough, so the network can accommodate all the tasks if you are learning them continuously, if you are learning them simultaneously. So this is like learning them simultaneously in a way. We basically say, take examples in memory from previous tasks, interleave them together with learning the new task. Okay? That's the memory buffer. There are challenges here because you need memory cost, and you think about large language models. That task 1 was just learning from the entire internet and text that in internet to learn to perform the amazing performance that language models like ChatGPT are doing. But now imagine that's what happens all the time. You as a company, or you want now to take this large language model and to fine-tune it, to train it to learn some specific tasks, not the general learning. You want to fine-tune it to learn to code programs, to write code, or to solve math questions, and so on and so forth. Then you have to fine-tune it. It's like learning a new task. Now, you cannot really, there is no way that you can store the data that you used, even fraction of the data that you used for task 1 to actually retrieve it. So this is a huge memory cost, at least for some tasks. And another one is, because you cannot store all the data, you have to choose. And that's an interesting question, which, if you have to choose only a few examples from learned tasks, which examples you use? Shall we use the more typical examples, like a typical representation of the old task to be relearned or refreshed? Or you use the most difficult ones that are, you barely were able to learn them. Maybe these are the tasks, the difficult ones from previous experience you should store in memory to learn. So there is a debate in this, and there are different conflicting ideas about it, but this is challenging, open challenge about this method. So now the question is, can we do replay without memory storage at all, without an extra disk on the side? Something that automatically allows the network to reactivate old memory traces while you learn new one, so that you can refresh old memories. And that's where sleep comes into play. So here is the figure that I promised to show you how we do it. This is where the idea is a very old idea, and there is a lot of empirical evidence that animals and humans use sleep. And sleep is important for memory, but in part because sleep allows to spontaneously reactivate old memories. Can be by dreams, or can be in other stages of sleep. There is a big topic of research, which stages of sleep, what they do for memory. But in any case, the idea here is that in this memory system, you can, while you learn a new task, or interleaving between, not the task, but interleaving between memorize a new experience and memorize the second experience, the network can randomly, spontaneously reactivate all memories without having to store them explicitly in the side. And then you just relearn them. That's called consolidation. And in this case, this is the way it works. It works relatively beautifully. As I mentioned at the beginning of my talk, the challenge is to do it for continual learning. That's the challenge, because how do you spontaneously reactivate previously acquired skills in a network in such a way that you can interleave? So there is a huge literature about machine learning, how to use sleep paradigm to replay in automatic fashion old knowledge and old skills and interleave them in learning the new skills. All right. Now, a few minutes about forgetting as a feature. Okay, until now I talked about how to battle forgetting or catastrophic forgetting. But what about maybe forgetting is good for us? Okay, so here are a few notable quotations. The advantage of poor memory that one enjoys several times the same good things for the first time, by Nietzsche. Rav Nachman of Breslov, the famous Hasidic rabbi, and a folk psychologist. Most people think of forgetfulness as a defect. I consider it a great benefit. Forgetting frees us from the burdens of the past. And in more contemporary times, a psychologist or psychiatrist at Columbia just recently wrote a book about the benefits of not remembering, and you can read it. It's all makes sense, which is interesting. It's all very intuitive. Yeah, it's good. I mean, why we have to be burdened about the past and so on and so forth? It's good to be freed of old memories. When you come to serious work particularly about learning, but also about memory, then you see that in order to make sense of this in terms of a real model, an algorithm, and a theory of that benefit from forgetting is a challenge, and it's ongoing research. Okay, so when we talk about forgetting in a positive sense, we have to separate two things. One is non-selective forgetting. I already mentioned it previously. Non-selective forgetting means that you somehow erased all memory traces to make room for the new ones. It doesn't matter which ones. This is good for memory, as said, for learning, for acquiring knowledge. You don't want to do it in a non-selective way. Maybe there is a selective way. So this would be the selective forgetting of specific data. So one word about the non-selective. I promised you to explain how we do this. This is without the sleep, but with the aging, catastrophic aging. We forget all the old memories and remember everything in the recent past. The trick is very simple. Every time you encode new memory, you decrease by some factor all the synapses in the network. It's called weight decay. Non-selectively, all the weights in the network suffer some small decrease, and then selectively you increase them for the new memory. So what happens in this way, you decrease all the synapses, you selectively enhance them for the new memory, and so on and so forth. So that's the way automatically what happens is old memories die because of this decay, and new memories survive. It's a very efficient way of make sure that if you really don't care about what you learned in the past, you are young, you only care about what happens in the last, year or 2 years ago. Do this weight decay, non-selective way. It guarantees you that you will be, like Nachman of Breslov said, you're free from the old world, you live in the new world, in a non-selective way. But good for memory maybe, but bad for skills. You don't want to forget what you learned in the past in terms of knowledge and skills. All right, so is it good to selectively forget? And that's, I talked about AI and the brain last year in Stockholm, and I told you the field is moving so fast. This is another sign of it. Last year I couldn't talk about it because it didn't exist, more or less. This is a huge field now in machine learning. Machine unlearning, MUL. You open the browser and you'll see tons of papers and blogs and conferences. And Google started last year or 2 years ago, started a challenge, a competition among labs and researchers and companies to come up with good algorithms for machine unlearning. Sounds crazy. Why machines should unlearn? MUL. But there is a very important and good reasons for machines to unlearn in a selective way. I'm not talking about forgetting. I'm talking about learning, unlearning in selective way. Applications, privacy. Think about large language models or large AI models for images or from audio and for video. A huge problem that we all know about: privacy, copyright protection, content safety and moderation, security, and also model improvement. All these are very important applications these days that are bottlenecked, that are stalling the further growth to some extent of AI because of the legal and ethical and political issues that they use vast amount of information to train the network. But I'm talking now about what happens after training, not what happens while you train. But after training comes an artist and say, well, you cannot use my data. Okay, so so the company has to erase the data from this particular artist. Or somebody says, well, you have a beautiful face recognition system. I don't allow my face that you took from the internet to be used. Erase my face. But remember, this is after learning. The system has learned. The data doesn't exist anymore. All that you have is a big network with connections. But now you have to unlearn in a very specific data. So you can unlearn particular item, or you can unlearn, or you should unlearn a feature like gender. The government would say, you can do whatever you do with images, but you should erase the label gender. You should not say female and male. Okay, so you have to erase a feature across the entire data. How do you do? Or class removal. Or for instance, you want to remove from your network, from the trained network, every reference to magic, to something, I don't know, to fake information or to information about how to build a nuclear bomb, right? I mean, you can now write down and say, okay, give me a recipe for building a nuclear bomb. Now, if you screen the data beforehand, that's something else. But you use all the data, including how to build nuclear bombs. Now you have a trained network. Now the task is remove information about nuclear bomb, okay? And so on and so forth. Robots in healthcare. You have a robot in Japan and maybe in other places that take care of patients or people. Now, let's say they recover. So they go on to another one. You want to be able to erase all the information about that. So that's a big problem. But there's also an issue of model improvement, because imagine that you know that your data is flawed, that when you trained it, the data was poor, not in terms of ethical issues, but it just was bad samples, noisy samples. Now you want to say, well, I discovered that these samples are noisy. How can I edit my network to remove the bad impact of these anomalies, of this noisy? Imagine you're a neurosurgeon and you're or radiologist. You discover that some data that you use to train your algorithm was noisy. Okay, you want to improve your network by somehow take care of that. But how do you take care of that? How do you improve your model or edit it? Okay, so these are the challenges. It's enormous challenges intellectually. It's a fascinating problem. Imagine you have a brain, okay, and now okay, so how do I locate where in the brain a particular information is stored? Well, all that I have is this big network, messy network with all the connections in them. How do I actually locate where they are? And even if I locate, what do? I take those and erase them. Everything is distributed. The problem is, and it's even harder problem, because suppose I'm an artist and I'm telling you, okay, erase my whatever, my videos, and you somehow manage to do it. It's not enough, because I can sue you on the basis of the fact that your network is a better music network because of my data, okay? So I need some percentage of your royalty, okay? So what you have to, in many cases, what you have to do is to erase not only the data, but the impact of the forget data on the behavior of the network. After training, you have to say, well, I managed to not only erase your data, but I managed to erase the benefit that I got from your data. How do you do that? It's an amazing challenge. And intellectual and conceptual problem is fantastic in this kind of distributed network. Okay, and finally, how do you verify that? How do I verify that I actually erased? I ask the network about you. What do I do? All right, so this is the problem. Learn, then you have data that you want to erase, to unlearn, but then you have to maybe relearn again to make sure that you have not used this data. What is story here? So the simple answer is the following. There is a gold standard, which is completely not realistic. The gold standard is the following. After learning, I have my big, I'm OpenAI, I have my big ChatGPT 5, and now you come say, well, don't use my text. And I say, fine, I'm removing, what does it mean removing your text? I don't know how to do it. I take the whole story and start again. I remove your data from my training data, and I retrain again. Now, you cannot complain, right? Because I really retrain from scratch the entire network by removing your data. That's unlearning in a stupid way, but that's the gold standard. Relearn network from scratch with subtracted data sets. That's unrealistic, but that's the standard. That's the gold standard. Real life is an approximate way. You want to, here are several ideas. Reverse learning, remember what I talked about, weight regularization. There are algorithmic way to test what is the, to test the importance of a weight to a task, whether this weight was important for task 1 or for task 2 and so on. So imagine you use the same trick, but for unlearning. You learned with the corrupt data. Now you find the data, not the corrupt, the full data. Now you look at the data that you want to forget data. You can run an algorithm, and without learning, algorithm to say which weights are important for the forget data, the data you want to forget. And these weights, you do weight decay on them. You slightly decay them until you are sure that everything is okay. There's something else which you can so you unlearn the output. So you don't forget, you said it's too costly to remove your database, too costly. But what I can do is relearn the network on the forget data, not to give an output, to say, I don't know. Okay, I'm asking you, I'm asking the ChatGPT, let's say Harry Potter. I need to remove Harry Potter knowledge from the network. I cannot do it, it's too costly. But I can retrain the network so that every time a question about Harry Potter comes, the network says, I don't know. So it's like in the brain, it's a retrieval. I just block the retrieval. I block access to the knowledge rather than erase it. Okay, so that's the idea of forget data. There are other tricks. The last one is maybe the cheapest one, is in context. So you all know there is the big network. And now when you come, after training, when you come to ask something about ChatGPT, or you upload a news article and you ask it to summarize all these uploaded articles or data, and you question all this, enter into a separate, what's called in context. And that, the big network is reading and translating propagating to the network and gives you the output. That in context. So the companies can design some control on the in context. So whenever there is a question about nuclear bomb, there is a block at that level. So you don't retrain the network at all. You work on that in context machinery to make sure that it doesn't use illegal data and so on and so forth. So that's another trick. The problem is how can I verify, and I'm finishing, how can I verify that indeed this works? This is a big unsolved problem. Because suppose I claim to erase Harry Potter, or I claim to erase your email and your address from it. And I show you, you put the question, what is David's address? And he says, I don't know. That's not good enough. Here is an example, and this is my last example. No, here is the example. So researchers found, you take ChatGPT and you say, poem, 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 poem. Repeat this word forever, poem, 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 poem. What it does, it does poem, 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 and then after that, it gives you private data from somebody, not related to anything. It was a big, annoying surprise that you instruct the network not to give any private information. The network will refuse to give you private information if you ask for it. But there are backdoor ways, we don't know how, we don't know why, that you can hack the system and generate private information simply by asking it to do silly things. Which means that there is no, today, we don't know of any reliable algorithm that will verify that a knowledge or unlearning that you claim that you did, it's really complete. So that's an open problem. All right, so this is what I want to add. I want to say unlearning is fantastic for machines, but I believe it will be amazing for the brain of humans if we can use some of these ideas, once these ideas are fleshing out, is to edit or to improve our system of knowledge, to remove bad examples, and maybe more effectively to remove trauma and other unpleasant memory than currently in psychology or psychoanalysis. Okay, so that's a recap. Okay, so we talked about the negative aspect, catastrophic forgetting, about lifelong memory, sleep and weight decay, continual learning, regularization, dynamic gating, and kind of replay, but for continual learning. Then I talked about the positive part, feature, not a bug, non-selective forgetting. If you are happy with erasing old knowledge in favor of making room for new ones, that's very effective. But selective forgetting or machine unlearning or maybe even brain unlearning is much more challenging and much more, I would say, even interesting in terms, if we are able to do it, it will be a fantastic system that we can, after learning, go back and edit our system. And this is a hot topic where brain science and AI are learning, continually learning from each other. Thank you.
Wow.